Hi, the topic of the presentation today is concrete aggregate. My name is Børge Johannes Vigum. I'm an adjunct professor at the Department of Geoscience and Petroleum at the Norwegian University of Science and Technology in Trondheim, Norway. I also have a position at Heidelberg Cement Northern Europe, where I am a senior project manager. Talking about concrete, the Romans already 2000 years ago were aware of the material concretus. As mentioned by Vitruvius some 25 years before Christ, he said that a powder material from the nature can do miraculous things. If it is mixed with lime and crushed rock, it do not only give ordinary building structures great strength, but even masonry made in the sea will be so strong that neither currents nor water can destroy them. So the Romans already 2000 years ago know about the materials, and we still have some remains of their structures. We also have the Pantheon in Rome, a fabulous building built more than 2000 years ago. And as you can see, the dome is 43 meters of height and all built of concrete. And it's standing still today. So concrete has been for ages. Concrete is a flexible material. You could shape it in the way you like, and it's very strong and very durable. In Norway, we have quite a challenging infrastructure. We have roads along the coastline, etc., etc. So in that sense, we are very dependent in Norway of using concrete as durable materials. Also, when we started to drill for oils in the North Sea, we needed some big structures. We built the troll platform. The troll platform has actually biggest ever movable structures in the world. And as you can see here, compared to the Petronas Towers in Kuala Lumpur, the troll platform is more than 400 meters high. However, comparing the Petronas Towers with all other buildings made of concrete in the world, you see that even Petronas Towers are relatively small compared to the latest, the biggest or highest building in the world, the Burj Khalifa Tower in Dubai. And the Burj Khalifa Tower in Dubai, with its 828 meters height, it needed more than 330,000 cubic meters of concrete, or equal to around more than 37,000 trucks of concrete to build this concrete structure. But what made it very special in this structure, that even though it was built in the sand desert of Dubai, they needed to import sand from Australia used in this concrete. Quite remarkable. So today we're talking about concrete, and concrete is the second largest global commodity by volume in the world after water. And every year we are casting some typical 3 tons of concrete per capita in the world, which equal to around 1.5 cubic meters. So that means up to almost 25 billion tons for the 7 billion population of the world. So it's very much. The figures from China, which you can see from 2011 to 2013, you can see that this is the use of cement in China for these 3 years. And those 3 years, 2011 to 2013, China used around 6.6 gigatons of cement. And if we can compare that to what is used the whole century in US from 1901 to 2000, they used around 4.5 gigatons. So in 3 years in China, they made more concrete, they commute more cement than in the whole century in US. So we see a big development of the use of cement and so let's look how concrete is built up. Concrete of course, is glued together with the aggregates, and the glue is the cement and the water. So a typical concrete mix could look something like this for 1 cubic meter. So you have the cement around 350 kilo. You could have a coarse aggregate, which could be a 16 to 22 millimeters particle size, almost 600 kilos. And you have the slightly finer coarse aggregates, 816 for instance, around 330 kilos. And then you have the sand fraction, which is a typical 0 to 8 millimeter, around 945 kilos. And then you add to the cement the water, so you will have a water-cement ratio, in this case around 168 kilos of water. And then you are adding up with this concrete mix. In addition, you could have some different admixtures, etc. And you're ending up with this concrete mix with a typical density of 2,380 kilos per cubic meter. And please note that you see here that the aggregate is a very important part of the concrete, as it counts up to 70 to 80% of the concrete. So this is the typical mix of concrete, and as you realize, the aggregate part of the concrete is definitely very important. So why is it then important to know about concrete aggregate? Well, as I said, aggregates are approximately 7 to 80% of the volume of the concrete. So the aggregate will be critical for the properties of concrete, both in the fresh state, in the setting period, and finally in the hardened state of the concrete. We'll come back to that. We also seen that concrete strength has increased during the last years with all the new infrastructures, the platforms, the bridges, the dams, etc. There are more demand on the strength of the concrete, and consequently the quality of the aggregates used in the concrete is more critical. And finally, we also see that today we have more focused on durability aspects. We want the concrete to last, like the Romans, for decades and longer. So we are looking into, for instance, freeze-thaw durability, and also there has been some particular focus on alkali aggregate reactions during the last 20 to 30 years in Norway. And please have a look at another presentation where I'm particularly focusing on the alkali aggregate reactivity of aggregates in concrete. It is also important to know more about concrete aggregates because there's an increased competition with other materials, and we need to look into the economical benefits of concrete materials, etc. And we also have realized that even though that we have a lot of bedrocks all around, we have also had in Norway a lot of natural sand and gravel after the Ice Age. But we are now realizing that many of those resources, they are depleting around the main markets, the main cities and so on. So we are now seeing an increase in use of crushed aggregates, even in the sand size fraction, which we call manufactured sand. And for these new crushed aggregates, there will be some new requirements and some new challenges as so typical aggregates for concrete. When we are talking about fine aggregates, this is what we call sand. By a geological definition, the sand should be less than 6 or 4 millimeters. But typically in the concrete industry, they are talking about sand less than 8 millimeters. So as I said, up to now, we have had in Norway, some typical natural sediments, glacier fluvial and fluvial sediments that has been used. But by using those natural sands, we do need to take the petrographic composition as it is received, because it will be a mixture of different rock types that have been crushed down and sorted by the glaciers and rivers and so on. But we have these typical gradings used in the concrete industry as a 0 to 4 millimeter grading, 0 to 8 millimeter grading and so on. And in addition to this natural sand that has been used for decades, we also now realizing that we are able to crush bedrock and producing manufactured sand from that bedrock. And then we have the coarse aggregate used in concrete. As I said, by definition of geological terms, coarse aggregates are coarser than 4 millimeters, but more typical in ready-mix concrete production, we are talking about coarser than 8 millimeters. We also could have used natural sediments, natural gravel, but it's more and more common to use crushed rocks for these coarse aggregates. And typical gradings could be in the range of 8 to 16 millimeters and 16 to 22 millimeters and so on. So what kind of factors will be governing the aggregate quality? First, we have the geological origin, of course, the bedrock, the type of minerals in the bedrock, etc. So that is the rock itself. Then we have for natural sand and gravel, we have the transportation and deposit conditions and so on, what have happened when the natural gravel and sand and gravel were produced. For bedrock and for minerals, there will also be some metamorphic processes, so there can be some contaminations and deteriorations of minerals, clay minerals, etc. So that is the geological origin of the aggregates, and of course in many ways it's different to do anything about what the geological has been. Then during the production and refining of bedrock into aggregates by crushing, screening, etc., the quarrying, the crushing, we have a lot of possibilities to increase and have impact on the quality of the aggregates regarding the shape of the particles, the grading, and so on. But even when you have produced your aggregate, you have to handle it and storage and so on. And even though you have produced a very good quality regarding shape and particularly a good quality regarding grading, when you are handling and so on, you're building up piles, there could be some segregation of the original grading. There could be some crushing of the grain, so you get some fines. There could be some contaminations and so on, both during the handling but also during the transport of the aggregates to the ready-mix plant. So there are many things that could affect the final quality of the aggregates. So in a summary, we can see that the inherent properties from the geological perspective are of course important. In Norway, we do have in general very good and strong both natural aggregates but also bedrock aggregates. But what is happening, what we are doing in the quarry to the final use is of great importance. And we need to have focused on the quality on the whole process. So we have to have expertise in the way we are producing or processing the aggregates, and we need a very good quality control all the way to ensure the quality of the aggregates. So when you have produced your aggregates, or you have got your natural aggregates or your crushed aggregates and you're using it into the concrete mix, the aggregate itself will influence the concrete properties in 3 different stages. So the first stage is the fresh state. The fresh state is when the concrete is plastic, is flowable, and you're putting it into the mold, etc., etc. You're pumping it and so on. The second state is the hydration state. That's a state when the concrete starts to get hardened, and you have a setting time until it gets hardened. And then eventually the final stage will be the hardened state, and then your concrete is finished and it's developing strength, and hopefully it will be durable. So let's have a look at those 3 different stages, starting with the fresh concrete. The fresh concrete is when you are mixing the concrete at the batch plant. You are bringing it out to the building site, and at the building site you want maybe to pump it, and you want to pour it into the mold, and you want it to be flowable. without any segregation, etc. So in that stage, the grading of the aggregates are of great importance, particularly for the sand. I will come back to that. And the grading will affect many parameters of the concrete. It will affect the water demand. The water demand is how much water you need to add to the concrete mix to make it flowable. And if you have to add more water, you have to add more cement, etc. to make it flowable. And that, if you're adding more cement, then you have a possibility of getting more shrinkage when the concrete gets hardening, because the cement paste is shrinking. Adding more cement will have effect on the economy, etc. So the water demand is important, and the water demand is directly affected by the grading. And of course the grading also will have effect on the workability, how flowable it is. You want it to flow, but you want it to be stable. You want no segregation with different fractions. And for instance, if you are adding air into your concrete, which you often do when you want to increase the freeze for durability, you want the air content to be well distributed, and you want it to be stable and robust. And the grading will have impact on all those factors. And there's probably nothing such as optimum or the best grading. It will depend on different rock types, different types of concrete, etc. But what is important is to try to have a uniform grading. A uniform grading, so you could have the same grading day after day, even though it's raining or it's sunny or so on at the plant. In order to have a uniform grading, it is very important for an aggregate producer to have a very good quality control system. So the grading is a very important property in the fresh state of the concrete. So a typical grading could be something like this. For a natural aggregate, it always will have this type of S-curve, as you can see here, with the S going, as you can see in this curve. And when you have this S-curve, that will lead to a higher water demand in your concrete. But maybe what is even more important is the variation in the fine content of the mix. As you can see here, down in the around from 250 micron and down, we're talking often about filler from 125 micron and down and so on. And if you have variations in this grading, that is of great importance for the properties in the fresh state. As an example, we have here from a work by Roland Seporitis. He finished his PhD in 2016 at NTNU in Trondheim. He looked at different types of aggregate, manufactured sands and so on. And he in this case, you can see that he took the same aggregate from 125 micron and coarser is the same grading, so it's not included here. But from 125 and down to finer, you could see he used two different fillers, two different fines. The orange one is crushed washed fines, while the green one is a crushed unwashed. So you can see that on 16 micron, the washed one has a less content of fines compared to the unwashed. And when you're coming down to 20 micron, this is very, very, very fine particles. And usually we are not measuring this fineness at all in our ordinary grading curves. You can see in this case, the washed curve got only 10% less than 20 micron, while the unwashed curve gets less than 20%, the double below 20 micron. And as you can see, it's a big difference on the slump or the flowability of the unwashed one. The unwashed one with a higher filler content get a much stiffer concrete compared to the washed filler, with a less content of the finest of the finest. So it has been shown that even though we do not measuring this on a regular basis, because we are not able to measure this by ordinary screens, we need to use centigraphs or something like that to measure this very, very fine grading curve, but they have very, very big impact on the concrete fresh properties. Another from Sweden, where they in a quarry, first they included the fines that were created by the blasting. So this is also a crushed sand used. When they included the fines from the blasting, they got a very stiff concrete. If they had the exactly same mix recipe, but they removed the fines from the crushing and only had the fines from the production, they removed the fines from the blasting. They only had the fines from the crushing. You can see they have a completely different flowable concrete. So this is very important to remember, that the finest of the filler in an aggregate will have very much effect on the flowability and the rheological properties of fresh concrete. In addition, in fresh concrete, you have the shape of the aggregate particles. Of course, you want to have more cubical particles will make the concrete more flowable, and you need less cement to let the cubical particles flow around. So cubical particle will always be better than flaky particles. In some Norwegian rock types, we do have a lot of mica minerals. Mica minerals like biotite and muscovite will be very, very flaky minerals. So when you're starting to crush down your bedrock, and particularly into manufactured sand and so on, you could increase the content of free mica. When the mica is inside the particle, there is no problem. But when you're starting to crushing free mica, the free mica particles will have a very high specific surface area because they are very flaky and very thin flaky minerals. So those thin flaky minerals, they need some more cement paste, some more to cover and so on. So free mica is a problem in manufactured sand, and it will increase the water demand, and it will make the concrete more stiffer and less flowable, etc. In addition, you have the water absorption. In Norway, typical granites, gneisses, etc., they have relatively low water absorption, around 0.3–0.5% water absorption. So that will not have so much effect in the fresh state of the concrete, but other countries, they have more porous aggregates, like volcanic aggregates from Iceland, sandstones in Europe, etc., where you can have water absorption of many percentage, and for those kind of aggregates, they will have some definitely some effects on the fresh property in concrete. If we continue to the setting time of course is only a few hours when the concrete is going from the plastic flowable state into the hardening state. But in that setting time, there could be some aggregate properties that could have effects on the concrete. First, if you are using a natural sand, natural sand could have some contaminations of humus or organic things, and those humus could have some negative effect on the setting time. They could have some retarding effect, that the setting time is postponed, take longer time, and that may also have effects on the final strength of the concrete. In addition, when the cement is setting, it's developing heat, so that the concrete get warmer, and we do not want the concrete to get too hot, because that could lead to cracking due to the temperature, and they could also lead to some other negative effects. So if you have a very massive big concrete like a dam or a very big fundament or something, there could be a big heat development in that concrete. And one way to reduce that heat development is that if you are using a more heavy aggregate with a more heavy density, then that heavy density aggregate will have a higher heat capacity. So that will, in a way, reduce the heat development in your concrete. So you could, in certain examples or cases, you could select an aggregate with a higher density to reduce the heat development. Then you have the final stage of the concrete. That's the hardened concrete. Then the concrete is in its final state and should hopefully stand there for decades, ages, and long time. So the strength, of course, if you have a strong, good aggregate with a good bond with the cement paste, you got a good strength. So the aggregate will, in most cases, have a direct implication of the strength. And also the E modulus. The E modulus is how kind of flexible the concrete is, or if it's bending down or not, and so on. If the M modulus of the aggregates will directly influence upon the E modulus of the concrete. And of course, you also want a good binding between the aggregates and the cement paste, and that will directly influence the strength and the E modulus. If you are using concrete as surface like a road or something, of course you want to have a high abrasion of your aggregates. But in most cases, if you are using it only as a structured concrete, the abrasion of the aggregate is not that big important. However, you want to have your concrete to be freeze-thaw resistance in areas like in Norway, where we have winter with freeze-thaw and so on. We want the concrete to be freeze-thaw resistance. In Norway, with very dense aggregates with a low water absorption, we see that most concrete, when you are adding some percentage of air, will be freeze-thaw resistance. But when you have some aggregates with a higher water absorption and so on, there could be some challenges with the freeze-thaw resistance. You also want your concrete to be dense in a way that will not crack, but also the cement paste and everything will be dense. So the chlorides, if your structure is close to the sea or you have some de-icing salts, etc., you want it to be dense to avoid the intrusion of chlorides, which eventually could affect the reinforcement bars, and you could have some corrosion and so on. And then finally, there could be a reaction between the aggregates and the cement paste in your concrete, leading to a reaction called the alkali aggregate reactions. I have a separate presentation on that on my YouTube channel. So I encourage you to, if you want more specific information about alkali aggregate reactions, you should watch that presentation where I'm much more in detail describing and explaining that reaction, which has been a problem in many countries around the world, leading to expansion and problems with concrete structures. So as a summary of this presentation, I have tried to emphasize the importance of aggregates in the concrete. Aggregate is the major part, or it's up to 80% of the concrete. So aggregate is not there just to fill in. It's the major part of the concrete, and the cement and the water is gluing everything together. So we have realized that the quality of aggregates and the properties of aggregates are very much influencing the properties and quality of the final product of the concrete. So in a way, you could see that inexpensive or bad quality aggregates could lead to an expensive concrete. Because if you have a bad quality aggregate, for instance with unhomogeneous grading, etc., bad shape, lot of free mica and so on, you will get a higher water demand, which requires more cement to be added into your mix. And you need that more cement to maintain a water-cement ratio and the strength requirements given for your concrete. So that will result in a more expensive concrete due to the higher amount of cement, and the higher amount of cement could also lead to higher potential of shrinkage. If you have a weak, inexpensive aggregate, that will also require a lower WC water-cement ratio, and you need more cement. And then, well, to maintain the strength requirements. And once again, you got a more expensive concrete. If you're buying a cheap aggregate, but it will have a lot of variations in the grading, etc., and so on, you need to lower the water-cement ratio. You need to increase cement to get your strength requirements. And once again, you get a more expensive concrete. And also, if you have uncertainties about the grading and so on, there will be more frequent concrete testing failure, which is of problem when you are testing the concrete as has been placed in a structure and so on. So the main message is that you should focus on the quality of your aggregates, even though the aggregate is maybe more expensive, of a better quality, but at the end of the day, it will lead to a better, but also maybe less expensive concrete. Thank you for watching this presentation. And as I said, please also look at the other presentation at my YouTube channels. Bye for now.